For this problem, we're going to take a look at these four sequences and find an expression for the apparent nth term for each of them. All right, for the first one, 4, 7, 10, 13, 16, 19. There's no pattern that always works for every one of these. Basically, it's kind of staring at it and seeing what the pattern is. For this one, I will see that if I subtract one, let me just do some scratch work down here at the bottom. If I subtract one from each of these, I would get 3, 6, 9, 12, 15, 18. And I recognize those are multiples of 3. And so it looks like this has something to do with multiples of 3. I take multiples of 3 and then I add 1 to get this. And so it looks like the pattern is going to be 3n plus 1. I take the multiples of 3 and then add 1 to them to be able to get this sequence. All right, so that's the solution for this one. In a previous class, you may have seen that this is called an arithmetic sequence, and there's actually a formula for that that you may have seen in pre-calculus for an arithmetic sequence. Here, I'm just kind of eyeballing it. All right, next one. 1, negative a half, 1/3, negative a fourth, 1/5, negative 1/6. All right, so let's kind of take this one back in pieces. So a sub n equals. Okay, clearly there's a fraction. Also, I see that I have a denominator on all of these except for the very first term. And so let me put the denominator there, 1 over 1. All right, now I can see the denominator has a clear pattern, 1, 2, 3, 4, 5, 6. And so the denominator is simply going to be equal to n for these terms. Now on top, I have a 1, negative 1, 1, negative 1, 1, negative 1. And so that clearly follows the pattern negative 1 to the n. Now, before I stop this, let me take a good look at this. If n is equal to 1, negative 1 to the first is negative 1. So that's not what I want here. I want this to start positive, not starting negative. So because I need this to start positive, what I have on screen now is not quite correct. I have to make a slight alteration. Negative 1 to the n minus 1. Let's see if I can get that to show up a little bit better. Negative 1 to the n minus 1. Now, if n is equal to 1, I have negative 1 to the 0 is plus 1, and it starts positive. Okay, so that is the second sequence. The third sequence, we have x squared, x cubed, x to the fourth, x to the fifth, x to the sixth, x to the seventh. So clearly, this is going to be a fraction again. I clearly see x to powers, and I see I have x to the first, x to the second, x to the third. So the power, the exponent, is the same as the term number, so x to the n. Now in the denominator, again, let me put over 1 over 1, and I notice I have the factorial pattern. 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial. Okay, now I notice that this, for the example for this last one, this one is 6 factorial, and the 6 here is 1 less than the exponent. And so that suggests that I should make this n minus 1 factorial. So the number in the factorial here is 1 less than what's in the exponent up here. Our last pattern, we have negative 1, 1/8, negative 1 over 27, 1 over 64, negative 1 over 125, 1 over 216. Again, let me put an over 1 here so I can see the pattern. So for this last one, I again have a fraction. On top, I have the alternating signs again, negative 1 to the n. And this time, because I wanted to start off negative, I'll leave this alone. So this one here, I had n minus 1. This one will leave as negative 1 to the n. On the bottom, I have cubes. 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, and so on. And so because all of those are perfect cubes, I can write the pattern as negative 1 to the n over n cubed. And I have an n here because when I plug in 1, negative 1 to the first is negative 1, which matches what I have over here. So for these problems where I'm finding the apparent nth term of a sequence, there are some techniques that work. Sometimes it's just a matter of eyeballing the pattern and trying to find something that works.